If you follow the math community at all, you may have stumbled upon the game of NIM, the game where two players take objects, or NIM in German, out of separate piles, and the last player to take an object wins. Wythoff's game is a variation of NIM in which two players remove objects on their turns. You're allowed to either remove any number of objects from one pile, or the same number of objects from both piles. The last player to take an object wins. As an example, let's start with a pile of 7 pieces and a pile with 5 pieces. A possible move in this position is to remove 3 pieces from the pile with 7 pieces. Another possible move you could make is to take 2 from each pile. Here's how a match in this scenario could be played out. Player A takes 4 out of the 7 pile. Player B then takes 2 pieces from each pile. Player A takes 1 out of the left pile. Player B takes 1 out of the right pile. Player A takes the remaining 2, winning the game. You may not be able to tell from this match, but there is indeed a strategy to this game. Let's break it down to find out. One of the best ways to understand challenging puzzles is to simplify the scenario. So following that, let's start with the smallest possible game, where one pile has 0 pieces and the other has 1 piece. In this match, there's only one possible move, which is to remove the piece from the pile. Since this position will lead to a guaranteed win for the player receiving it, we'll call it a hot position, because you win. Let's move to the next biggest position, where both piles have 1 piece. Before I explain this position, I want to emphasize how in order to create a successful strategy, we must assume both players are playing optimal moves. So while the player could just remove 1 piece from one of the piles, a player playing optimally will take 1 piece from each pile, which would win them the match, thus making this point another winning point. Next, let's try a match where one pile has 1 piece and the other pile has 2 pieces. You may notice that there's not a guaranteed win in one move from this position, meaning this position cannot be a winning point. Now we can analyze all the possible moves in this scenario. If you remove the piece from the pile with 1 piece in it, the other player is given a position where they can win in one move. Similarly, if you remove 1 piece from the pile with 2 pieces in it, or remove 1 from each pile, the other player is given a winning position like the ones we just labeled previously. Since every possible move in this match will lead to the player receiving it to lose the game, we'll call this position a cold position. Skipping a few positions, the next losing point can be found when one pile has 3 pieces and the other pile has 5 pieces. In this position, unlike the last losing position, not every move will lead your opponent to an instant win. However, an opponent playing optimally will notice that no matter the move you play, they can either win the game or bring the piles down to 1 piece and 2 pieces on their next move. Since we just showed you that position is a losing point, then regardless of how you play from the initial position, your opponent will eventually win the game, therefore making this position another losing point. If you continue to discover winning and losing points, you'll get a list of values that look like this. While the pattern between winning points is fairly obvious, the losing points just seem to be random sequence of values with no apparent relationship. We'll touch more on that later. Instead, let's go back to the first game with our newfound knowledge. What are the best moves in a game with 2 piles of 7 and 5? Cold positions allow us to play this game optimally. There's actually 2 ways to win in this position, and we've already shown you one of them. The first way to win is to get into the 3-5 cold position. If you're player A and you take 4 stones out of the 7, then player B will now be in the 3-5 cold position, and thus lose the game as we discussed earlier. The next way to win is to get into the 4-7 cold position. I will leave this as an exercise to the viewer because otherwise the video would be way too long, but I seriously implore you to go try figuring out for yourself. If you go first and get player B into the 4-7 position, is there really a way for player B to win? Spoiler alert, there isn't. So, therefore, there's actually 2 ways to win in this position, 3-5 and 4-7. The optimal strategy is to lead your opponent into a cold position, This allows you to take full control of the game and win regardless of what your opponent does, provided you play smart and keep leading them to more and more cold points. Let us return to the losing point table. Notice that the difference between the number of pieces in each pile is increasing by 1 with every losing point. This could be important, so let's add it as another column in our table. Now, let's make 3 graphs with each combination of values. We have filled the table with more values of cold positions, but feel free to experiment yourself. First, we'll graph the smaller pile on the x-axis and the larger pile on the y-axis. While this collection of points may not mean anything to you at first, if you graph the line of best fit, then you'll find that as the number of terms increases, it's approaching a number that should be familiar to most of you, that being 1.618,03399, or the golden ratio. This on its own is already an interesting discovery, however, it only gets more interesting as we keep graphing. Next, let's graph the difference between the piles on the x-axis and the smaller pile on the y-axis. Interestingly, the slope off this graph also approaches the golden ratio, but this time with a y-intercept. We'll let you interpret what the y-intercept means, because we're not going to cover it in this video. Lastly, let's graph the difference between the piles on the x-axis and the larger pile on the y-axis. This time, the slope of the graph approaches a new number, 2.618,03399, and as it turns out, this number is actually the golden ratio squared, meaning all 3 relationships derived from the losing points have a correlation with the golden ratio. In order to understand just how strong the relationship between the losing points and the golden ratio is, let's compare it to the golden ratio's derivation from the familiar Fibonacci sequence. Many of you may know the Fibonacci sequence already, but for those who don't, it's a number pattern beginning with 0, 1, 1, 2, 3, 5, etc., where the nth number in the sequence is equivalent to the sum of the 2 numbers before it, meaning that the next number in the sequence would be 8, because 5 plus 3 is 8. The one after that would be 13, because 8 plus 5 is 13. Now, the golden ratio is derived by stating that the ratio between different pairs of consecutive numbers in the sequence eventually approaches the same value. If we want to write that out numerically, we would say that x sub n over x sub n minus 1 equals x sub n minus 1 over x sub n minus 2. And both of these ratios are equivalent to some value, let's call it phi, because that's how the golden ratio is usually denoted. We know that x sub n is equal to the sum of the 2 numbers that came before it, those being x sub n minus 1 and x sub n minus 2. So let us insert that into our equation. Now we have x sub n minus 1 plus x sub n minus 2 all over x sub n minus 1, which equals x sub n minus 1 over x sub n minus 2. If we simplify this fraction here, we notice 2 things. One is that x sub n minus 1 over x sub n minus 1 is simply just 1. And 2, since x sub n minus 2 over x sub n minus 1 and x sub n minus 1 over x sub n minus 2 are actually reciprocals, and x sub n minus 1 over x sub n minus 2 is phi, they can be rewritten as 1 over phi and phi respectively, thus making our new equation 1 plus 1 over phi equals phi. If we multiply both sides of the equation by phi, then by moving all our terms to one side of the equation, it will be simplified into a form that should be very familiar to most of you. Now, as you may have guessed, we can use the quadratic equation to solve for phi. Our a is 1, our b is negative 1, and our c is also negative 1. So we can fill those values into the quadratic equation to get an expression that simplifies to 1 plus or minus root 5 all over 2. If we add, we get the familiar number 1.618,03399, which is the golden ratio, and if we subtract, we get the number negative 0.618,03399, which happens to be negative 1 over phi. Surprisingly, the golden ratio can be derived in a similar way from the losing points in Wythoff's game. By analyzing our original table of values, we can derive the equation that the larger pile, L sub n, is equal to the smaller pile, S sub n, plus the difference between the piles, n. N just so happens to be determined the sequence as well. From our graphs, we know that the slope of these two lines are the same. Since the slope of a graph is approximately equal to its y value over its x value, we can write the equation L sub n over S sub n equals S sub n over n, where both ratios are equivalent to some number phi. Since we just derived the equation L sub n equals S sub n plus n, we can insert it into the equation and get S sub n plus n over S sub n equals S sub n over n, which can be rewritten as 1 plus 1 over phi equals phi. By now, you may have noticed the similarities between our two derivations, and if we keep deriving, we'll get again negative 0.618 and 1.618. This means that the Fibonacci sequence and the losing points in Wythoff's game have the exact same relationship with the golden ratio. This is extremely significant because the Fibonacci sequence is typically credited as the sequence with the closest relation to the golden ratio. For those of you that are more curious, it gets even more interesting when you put the losing points into an infinite matrix known as Wythoff's array. You may have noticed that some of the losing point pairs represent consecutive numbers in the Fibonacci sequence, namely 1, 2, 3, 5, and 8, 13 in the first few pairs. If you analyze further, you may notice that the pairs that aren't included in the original Fibonacci sequence follow the same exact pattern, like 4, 7, 11, 18, and 29, 47. In fact, every cold position pair can be found in one of an infinite amount of Fibonacci sequences, suggesting that the losing points in Wythoff's game are more related to the Fibonacci sequence than the Fibonacci sequence itself. So what did we learn today? We saw a very cool way the golden ratio pops up in a game of taking stones out of two piles, a game which has been played for thousands of years. We explained the rules, analyzed the best strategies for winning, coming to the idea of hot and cold positions. We then showed that this idea has very close ties to the golden ratio in not just one, but 3 different ways. We used a very similar derivation of the golden ratio from the Fibonacci sequence to show that the golden ratio occurs in the losing point graphs. Finally, we briefly looked at Wythoff's array, which shows that Wythoff's game may be more related to the Fibonacci sequence than you thought. This video was to highlight one of the beauties of math. Nobody knows why the golden ratio appeared in this game, but it just chose to. And that, to me, is fascinating. I hope you found this video interesting and have a fast day.